Welcome everyone. Quantum computing is not the end. It could be the beginning of something more profound like quantum computational neuroscience, where the intersection of AI, quantum, and the neuroscience comes in, and this synergy can potentially push the limits of computing beyond the limits of what we can achieve. The major part can be simulating the brain functions and how the brain computes things. Also, we can benefit from the neuroscience knowledge and the way that neuroscience works in enhancing the quantum algorithms and the quantum machine learning algorithms, and use this knowledge and the way that the brain computes to make computations using quantum computing much more efficient. So with quantum computing, we hope to simulate quantum systems like chemistry and also biological systems. And also, we want to simulate the brain itself. And here is the thing where the AI and the neuroscience comes together to unlock new potential in the future. And this year, the Nobel Prize in Physics was awarded to a profound work for the superconducting circuits that gives the birth certificate for the qubits, where the three Nobel laureates have been awarded the Nobel Prize in physics for their profound work and superconducting circuits that enables the superconducting qubits technology. Of course, there is a separate video that talks about this, and now we have two bright guests in the show. We have Dr. Eva Andres and also Cierra. And Cierra is a strategic content director at Quantum Insider and the founder and the CEO at Universum Labs. Eva is a professor of quantum AI at the European University of Madrid. And together we are going to explore quantum tech, quantum AI, and also quantum neuroscience and the future trends of this field. Welcome, Eva. Welcome, Cierra.
I'm happy to be here. Thank you. Happy to be here.
So we are now in the NISQ era. For our viewer, typically we have two types of qubits. We have the physical qubits and we have the logical qubits. Of course, physical qubits are the ones that we use in the lab. Those are the actual qubits that are being realized in the lab and what we actually do computations with. Logical qubits are the ones that use in algorithms and the ones that we use them as an abstract. So they are perfect qubits. They are the abstract ones that we use in everyday conceptual use cases. Physical qubits are prone to errors, and hence we use error corrections in which a group of physical qubits are being grouped together to represent one logical qubit. With this technology, there is several schemes to do the things like gross code of IBM or the surface code of Microsoft and several techniques. However, with these current technologies, hopefully we achieve sufficient number of logical qubits after corrections. That's enough to do useful computations, because now in the NISQ era, the number of logical qubits after corrections is not enough to make computations useful, like Shor's computations, or even performing chemistry simulations that require thousands and thousands of qubits. Okay, so there is path for fault-tolerant computing, and according to IBM roadmap, we achieve this by 2029 or 2030, and hopefully we have a meaningful computations at this time. However, the question comes in how we can enhance the physical qubits and how many physical qubits will be available in order to achieve this number of logical qubits. IBM and the several companies have demonstrated the first quantum, or the aim to demonstrate the first quantum computing advantage in next year. However, recently Google Research has announced a verifiable quantum advantage using several qubits in their Willow chip. And with this verifiable advantage, they show that, of course, it might not be a practical use case. However, with this, they show that they can surpass the capabilities of current super classical computers with quantum computers and show a verifiable quantum advantage. Then we hope when the quantum computers are ready to have a potential for chemistry and physics simulations that will flourish, and this will enable applications like quantum AI. So now we come to Eva. How do you see the future of quantum AI in the fault-tolerant quantum computing era? and what will be these potentials or what will be the potential applications?
Okay, that's a great and very timely question because, as you mentioned, recent advances in quantum computing, such as milestone recently done by Hugers, demonstrating quantum advantage, announced last week, are a clear sign that we are closer to this era, quantum, full quantum era, no? Okay. And when we reach this era, I see quantum AI will finally go beyond a small data set and small experiments, toy models, and to real world application, no? And will be able in this era to build and to train more complex models, more complex circuits, using reliable qubit and using more stable qubit that we can perform better algorithm, more intelligent algorithm, and also prefer models more complex, like such a emulating brain dynamics, no, brain intelligence, and emulating, no, the brain functionality in this algorithm. I see three main directions. The first one about quantum in-phase machine learning, because the quantum model have the potential, as we know, to learn some fewer data than the classical ones, and for that generalize better than the classical ones. And we can see this potential in early benefits using quantum simulators, because this model work in Hilbert spaces that are more complex and richer than the classical flat space. But the real potential we can achieve using quantum computer fault-tolerant, no? We can use the superpositioning and the entanglements with its real potential, no? And the second one, building this complex system, for example, multi-agent system, combining quantum agents, classical agents, and hybrid quantum agents, for example, in small cities, use cases, and also in rescue site system, no? With these agents collaborate, among others, sending message, and the behavior is more similar, emulating human behavior, human collaboration, human intelligence, social intelligence, more rich than we can imagine currently. Now. And finally, I think the most bigger advantage we see in brain-inspired algorithm, no? Using and emulating the complex dynamic in the brain, the different paths inside the brain. For example, since we capture stimuli, working memory, how this memory work, the long memory work, episodical memory, and so on. And also when we make decision, no, the decision-making process, emulating the limbic system, and also the motor and the basal ganglia, no? All the connection amongst the different neural network, the synchronization, the plasticity, the communication between them, finding the optimal path to the final solution in our brain. We can emulate this using quantum computer, no, reliable quantum computer, because emulate this using classical hardware is almost impossible, because unless you're using, of course, is PC, high performance computer, no cluster. They can accelerate this experiment, and you can build more complex model, but in other case, it's impossible. So quantum computers can help us, and also, as we can see, more complex dynamic and more cognitive behavior our brain. For example, when we decide, or when we reasoning, or intuition follows more quantum probability theory than the classical ones, no? And we make decision or intuition or solving problems using quantum logic than the classical logic, no? Reducing response time. So we can model because this behavior, the cognitive behavior, fits better with quantum mechanics than the classical ones. No, can be explained better. It's in quantum cognition.
Yeah, thanks, Eva. And then regarding this, how do you see the quantum advantage in quantum AI? Would it be more accuracy or more speed or both?
I think both of them. For example, more speed compared to quantum simulator, because simulators emulate quantum operation using classic hardware, no? But at the same time, we note our algorithm improve in the accuracy and also in the convergence, using fewer epochs, fewer iterations than compared to classical AI, no? But also we get better accuracy, better generalization, better metrics due to the same reason, because we are working in Hilbert space. These space are more expressive, and we can also represent and check several solutions, multiple solutions, so we can achieve better better solution, better patterns, detect subtle patterns inside the data that the classical one simply can't. No, it's impossible not to detect it.
Okay, so that's always great to hear. So now we move to Cierra. So Cierra, now we are on the peak of the International Year of Quantum Technologies and Quantum Computing. So there's great interest indeed. So do you see the same continuation of the interest in the upcoming years as much as we have this year, or it will decay?
That's a really, really great question. I think one of honestly, one of the biggest benefits of having the International Year of Quantum was the visibility that it created and the awareness. There were a lot of global communities that really stepped forward and got newcomers involved, and I think that's really, really important. But what will be even more essential as we move into the new year and we don't necessarily have this overarching initiative to tie it back to, it's really going to come down to those of us in the community who are very passionate about developing the technology. I fundamentally think it will be up to us to really keep the momentum up to develop the ecosystem. And I also think another part of this is we really need to see more on the commercialization side, because the more that we have the interest of these really large hyperscalers who are doing quantum compute as a service, or we have just the really big hardware providers that are partnering quite broadly and quite globally, then it really starts to capture attention. And when you have attention at that global level, then you get the policymakers involved. And when policymakers are involved, then the general public becomes more involved. And so I think that the initiative itself was important to create this foundation of awareness and visibility, but it will really, really be up to us as a community to continue it forward, or else it does risk fizzling out. And quantum is very, very unique and special in that in order to develop the technology in the way that we would like to, it is going to take a lot of time and a lot of money. And so we need a lot of visibility for that.
So do you see then the quantum computing would still occupy the same interest in the media even in upcoming years?
I really, really hope it does. From a market perspective, we do expect the market to have quite large and consistent growth. And as long, again, I think it comes down to funding fundamental science. Because as we saw, if we look back at the Nobel Prize, for instance, so the Nobel Prize this year is really interesting. And it really highlights a very specific point, which is this is based on a paper that was published like somewhere around 40 years ago. And that paper was the foundation for the quantum hardware that we have today. So it took 4 decades to take this development in theory, this breakthrough in theory, and to get to the spot that we are today. And so in order to continue to drive quantum computing forward and keep it relevant, then we really need to continue with the visibility and the awareness, because again, we need the buy-in from the public, because this is not a short-term game, it's a long-term game. If we can do that, if we can be patient and we can work on long timelines, I do think we can continue to keep it relevant in general. But it will be an intentional effort, not something we do passively.
So that's great to mention, because now we see of course, the Nobel Prize recognition of the birth certificate of superconducting qubits, and then we wonder why we don't have the same achievement for a new computing, for example, for new computing hardware like the brain-based or a neuromorphic-based computing. And now we can just see this question. There is a lot of people think, okay, maybe quantum computing could be used as a tool to simulate the brain. And there is another camp who thinks that the brain itself could be a quantum computer. However, we didn't figure out how it works as a quantum computer. Of course, it's pretty efficient. It's almost about 10 watt, and these 10 watts we almost use for everyday computations we do and every tasks. However, this is different from the current technologies, where these technologies like superconducting or neutral atoms and many more, they consume, of course, significant thousands of watts every day in order to operate. So with this, we see also algorithms that leverage the neuroscience knowledge now, and of course, like the work with spike algorithms and all of this momentum around the quantum neuroscience. So the question comes now, forever, how we can benefit, or we can the quantum computer can benefit from the neuroscience in order to be a better architecture for computing.
Okay, it's a very fascinating question. I think both sides, because both quantum computer and brain works together, work in multidimensional space, such spaces, so we can fit problems in the same way. It's cool. For example, we can emulate in our brain the intuition, no? How we can make decisions shortly, reducing response time, using shortcuts, no, in this decision, or reasoning or solving problems. We can emulate it with quantum computing, with quantum algorithms, how we brain runs work at this way. And also we can emulate the concision, you know, when stimuli arise to our brain, they compete to reach the concisions, no? We can emulate it using constructive and destructive interference, no? So this fits better with quantum theories than the classical ones, because when we make a decision, the probability that we decide something always remains constantly if we use the classical probability lot, but this not happen. Some experiments doing about when we make decision, when we choose several options instead of other, demonstrate that depends of the context, depend of the new information arrives to complete other events, and so we can change or choose, no, or outcome. The probability doesn't remain constantly. So we violate the classical laws, no? And this cognitive process can be emulated better using quantum probability theory than the classical theory. So this cognitive process we can emulate in using quantum computing instead of classical hardware. And also when we decide something, make decision process, the different choices remain exciting in uncertainty in cloud, in some cognitive system superposition, cognitive system, and when we decide to choose, this system collapse to one option, no? Of this several options or decision, no? This model obviously with quantum computing, with quantum algorithm. In other sense, quantum computer, secondly, we can get inspiration from neuroscience, because recently paper published this summer, very interesting paper on neuroscience, It demonstrates that neuron in premotor cortex, which also navigate in multidimensional spaces, so quite better with quantum computer in hybrid space, can synchronize and find together this neuron the optimal path to the optimal solution. Without explore exhaustively all the possibilities, without lose in the high immense space, looking for and finding the solution. So we can get inspiration, for example, for solving Marren-Plateau's phenomena, that we can, when the learning can be stuck and no evolution and no learning happens in this point, so we can get this learning and introducing a quantum algorithm in order to be more efficient searching, navigating in the search space, no? More efficiently without exhaustively looking for all the possibilities, all the paths, no? Be more efficient in this.
So that's great. So we leverage now how the brain works and also the neuroscience and the neuromorphic based algorithms to make computations more efficient and also optimization problems. But now for Sarah, how do you imagine the brain really as an actual quantum computer, or this is being hyped a bit?
Oh, thank you. So neither. So I have a bit of a different answer. So I think that what we see with the brain, so far, what we know about the brain is that the brain could very well exhibit these quantum effects in either microtubules or other subcellular structures, which is really theorized by Penrose and Hameroff. And we did see evidence of this. Now, it might not be a literal quantum computer in the sense that we think of the hardware that we have today, but I think this speaks to a more subtle point, which is if we look back at the original computer and we compare it to today's supercomputers, these look incredibly different and they do function different, but we had to start somewhere. I feel very similar about the trajectory of quantum technology or quantum computers. I don't necessarily think that tomorrow's fault-tolerant quantum computer will necessarily resemble the quantum computers we have today. And so perhaps what we do see in the brain is a version of quantum computation that we are not yet fully, we don't yet fully understand, if that makes sense.
Yeah, definitely. I also agree with your point. I mean, Roger Penrose already many times was proposing these micro tuples, and of course there is one recent paper try to propose that you have seen these micro tuples somehow in their experiments. So we come into this point that the actual quantum computer in the future that brings value might differ from what we envision today as a hardware. So that's pretty, I think, important to mention to the audience. So now we come to, if we switch the gears, for example, to more proactive ideas, that of course the brain itself might harness quantum energy to work or work with quantum mechanics. Of course, the brain itself is a classical system, so otherwise our brains will differ in place. So it's still exists in our head indeed. However, the idea that we have a classical system that inherits a quantum nature and works with that, what would be the core argument that the brain even is an actual quantum computer? Why it's not a statistical classical system that of course lives on a top of quantum systems like a water, fluid, or a solid? So do you have any perspective on this? So we can start with Eva and then we'll get your perspective, Cierra.
Well, quantum computer particularly suited for problems that involving complex, high-dimensional spaces, as we mentioned before, or massive combinatorial search, for example, planning routing, scheduling problem, and so on. And finally, the quantum behavior, no? For example, nature, simulation, quantum, chemical, physical, and so on, no? And also the brain, no? Because have several behaviors that emulate better using this in the quantum mechanics. So, but related to the with the difference path, different fields, because we can emulate this quantum behavior, this quantum cognition, no? The quantum system that we have made decision, intuition, or consciousness works, But there are other that you mentioned before about our brain is a quantum computer, no? Related to this is a theories, Penrose theories, that have not been demonstrated yet, have not any evidence about that. So I'm more close to use the quantum cognition, no? How to emulate it, this process, this brain mechanics, the brain behavior, or human behavior using quantum models, no? So I see quantum computers can be better preparing, building a more complex model, for example, emulating the prefrontal cortex, the working memory, and so on, using quantum computing, getting the potential of superposition, entanglements, interference, that is not possible using classical computers, no? And this is very, very positive, no, to build these complex models, no, and emulate this cognitive behavior.
So that's interesting indeed to explore. So what do you think, Cierra, about this? Do you think also we have a quantum brain and Penrose hypothesis is well supported? Maybe parts of the brain could be quantum, the other would be classical, or what do you think?
I love this question. And so when I think about, for instance, if we wanted to simulate the brain, we would quite naturally need a system that could handle massive parallelism and also nonlinearity. And so both of those are quite easily those are very much hallmarks of quantum systems. So if we think that in order to simulate the brain, we would need something like a quantum computer, then I think it's fair to say that quantum has plays a large part in the overall function of the brain itself. And I definitely think that I really, really am interested in the Penrose-Hameroff theory. And I think that because we do see the evidence of the microtubules, which they had originally theorized, that I think it's very, very likely that there are quantum effects that are happening. It's just a matter of what does it lead to? So is thought itself some sort of decoherence? Is it an interaction between the possibilities and then there's this collapse into decision or insight? I think that overall, my answer to your question is I do think there's something there. I do think there are quantum effects in the brain. I just think we need to do a lot more work around exactly what part that they do play in the brain, because as you mentioned, it is very classical. We have a very classical experience. So at some point, the brain is not fully quantum, but there are definitely quantum effects playing a part there.
And that's pretty fascinating if we think about it, because we have this hybrid system that works, but we don't know how it fully works, as you mentioned also earlier in the episode. I see it as pretty fascinating that we need really quantum computer to simulate the brain. However, we still have a classical system that floats on this quantum realm somehow and benefits from this collective effect of quantum phenomena in order to produce what we feel as our awareness and our computational thinking as well. So, Eva, what do you see as a expected major breakthrough that could happen in the field of quantum AI or the brain-inspired computing in the next 5 or 10 years?
I see during the next 10 years or 5 years, I see more complex algorithm is getting inspiration about the brain, including this cognitive behavior that follows quantum mechanics than the classical ones. We can build more complex algorithms that can solve problems and working together with neuroscience in both spheres, and also using the insight of quantum computing, AI, neuroscience, physics, to using and these ideas to prepare to build more complex algorithms. No? So I see in this idea multiple agents working together, using collective intelligence, collaborating together, and also not in a collaborative way or just an agent, that's an AI, but incorporating to the algorithm more cognitive behavior, exploring the different areas of the brain and also the connection among the different neural networks and also non-neural, for example, like astrocytes or other neurons first that can improve the memorization, have a role in this memorization of our cognitive process. So I think there are many complex areas to research related to neuroscience and neuropsychology, and we can include in our algorithm to be more intelligent. These algorithms become more.
So yeah, that's interesting. I'm myself interested in of course simulating the neurons with quantum chemistry as a system with input and output. Indeed, if we can do such simulation successfully, we can learn more about the neurons. There is now a lot of companies who are trying to sell some offerings about computing using an actual biological neurons that, for example, they grow in the lab, or maybe they extract from animals and so on. So, how do you see this Sierra in the future? What do you see? How do you see this work? And also, the second question is about the ethics of extracting such biological samples and doing something with it.
It's a great question. So to answer the first part, I do think it's quite plausible that we will see an intersection between quantum neuroscience and biophysics. Definitely, it would make sense that in order to further understand biological systems, we would want to understand how do they potentially exploit like coherence for sensing and communication. And if we have the potential to translate those mechanisms into algorithms or hardware, then it could definitely play a part in the future of computing in medicine. And I think that the ethical guardrails question is very important. And we've learned so much from the development of AI. And the number one thing that we've learned is that we really need to start thinking about ethics very intentionally before the technology arrives. So if quantum computing does have this potential to intersect with neuroscience, so thinking about brain-machine interfaces or cognitive simulation, then we need to start thinking about issues of autonomy, of privacy, of consent. So who owns your neural data? That's a really important question to ask. And then what happens if a model has your cognition? So 100% we need to be cognizant of what the implications are, and we should start thinking about these things now, not after the technology already exists.
So that's a nice note, because all the time the technology just emerges, like what we see now with AI, and then the strategies and the ethics framework, they come after that, and then there is no more room to fix things that are not being fixed. Indeed, so that's interesting. So Eva, for you as a young scientist now, you explored a lot of things about the quantum AI. You do for research with brain-inspired or neuroscience-inspired quantum algorithms to enhance the computations and so on. So for that, what will be for a young student or a researcher passionate about this intersection? What advice would you give to them? What kind of skills or knowledge they need to acquire or to learn right now in order to proceed in this field?
That's an interesting question and very useful for the younger researchers. I say the most important thing is stay up to date with research in these different areas. Neuroscience, physics related to quantum mechanics, obviously, and also AI, because the inspiration could be from the different areas, and the eureka moments could be of different areas, because you can fit this idea and join the points. Oh my God, this problem it exactly happens in AI, not only in neuroscience, for example, or in physics, because AI gets inspiration from physics, from nature, from neuroscience, neuropsychology. So AI gets inspiration from everything. So my advice, get a day, stay a day with reading paper about these different disciplines, is my advice,
So that's really great to hear. With that, I know that the topic it just is infinite. I mean, we cannot, of course, contaminate it in one episode or complete a discussion about it. So hopefully, we have a few more future episodes to discuss about the brain and quantum brain and the quantum-inspired algorithms for the brain simulations and so on. But for now, I would like to thank you both, Eva and Cierra, for having you and being present in this podcast. And it was a great pleasure having you and also speaking about these interesting topics and how researchers and also the research and the industry can benefit from the new technologies and the new technology trends in new ways, especially with the intersection between the brain sciences and neuroscience and AI and the quantum AI as well. So thanks very much for being here, and look forward to hosting you in future episodes.
Of course, my pleasure.
Look forward to it.
Yeah, thanks.